Hello, we are Team 11, composed by Maria Eugenia Galina, Alejandro Gonzalez, and Shuna Casone, and this is estimation of obesity levels based on eating habits and physical condition.
From the original dataset of 17 variables, we are only using 8 to test our hypothesis: gender, weight, height, frequent consumption of high caloric food, consumption of alcohol, time using electronics, physical activity per week, and level of obesity. It is worth mentioning that for our variable time using electronics, we are referring to the time where most of our attention is directed to the device and its content, keeping the person in a mostly sedentary state, such as video games, phones, TV, and others. In case more detail about the original variables is required, there is a link in the description of this video. The label level of obesity was determined by calculating the mass body index, which is defined as the weight divided by the square of the height. We decided to use these calculations as a continuous variable.
For our first scientific hypothesis, we propose the following. Demographic characteristics such as gender of a person can have an effect on their body mass index, or BMI. Then we have our statistical hypothesis. As null hypothesis, the average BMI in males is smaller or equal than the BMI in female subjects. And an alternative hypothesis, as the average BMI in females is smaller than the BMI in male subjects. We can see that the variables involved are the BMI, that is a continuous variable, with units of kilograms over square meter, and gender, that is a categorical variable, either male or female. We can see that the BMI has some skewness to the right, shown in the histogram, and we found 12 outliers that can be seen in the box plot in the right. Given that our dataset has 498 observations, 12 outliers represent 2.4% of the dataset. So we will not consider these data points in future analysis. We know that BMI tends to be skewed by definition, so therefore we will test for a log normal distribution. We can see that within the diagnostic plots, using the R-risk distribution library from R, we can see that the log normal distribution is the best fit for our data. In order to confirm that the data follows a log normal distribution, we perform the simulation. The simulation process is shown in the following diagram. First, we resampled our data, having each sample 100 observations with replacement. Then we calculated the log likelihood for normal, log normal, and logistic distributions, as these three seem to provide the best fit. Then the best distribution was determined on the maximum log likelihood. For example, in here we can see that the log normal distribution has the maximum log likelihood, and this was repeated 1,000 times. As we can see from the results on the right, most of the samples, 985, had a log normal distribution. Now here we show the log normal distribution parameters that are the average, mu, and the standard deviation, sigma, and where m and s are the mean and the standard deviation respectively of the variable y, that is a natural logarithm of our data points. In order to get the Kramer-Rao lower bound, we first estimated the BMI average by calculating the derivative of the log likelihood of the probability density function of a log normal distribution, and by calculating the second derivative we can obtain our information matrix. Here we can see that mu had an estimated value of 3.17, and the Hessian for mu is 14,232.96. Then the Kramer-Rao lower would be the inverse of this I of mu, that is 0.00007. We also perform a simulation by having 1,000 samples with replacement from the original data, as well as 1,000 randomly generated data from oral norm. Each sample had 498 observations. For each sample, we computed an estimate of the average, as well as the square difference with a previously calculated estimate. We can see from the graph that around 70% of the samples has a lower bias than the CRLB of 0.00007. Both graphs of the resamples and the randomly generated data were very similar, so we just added the the randomly generated data here. As for the variable distribution of gender, this variable in the survey was strictly binary, meaning that the answers were female or male. And with this information, we can confirm that this variable follows a binomial distribution, given that each subject is considered an independent event. On the right, we can see a frequency table where from all our observations, 227 were female and 271 were male. So 45% were female and 54% approximately were male. Here we can see the normal distribution of the parameter of the average of BMI. So in blue we can see the normal distribution of the average of females, and in red we can see the male distribution of the average. The estimated value for the average in females is 3.14 with information function of equal to 7,168.89. If we plot this distribution as follows, we can see the result in the blue graph, and in the red is the same, just that the estimated average was 3.19 and the information for mu is 7,361.6. And here we can see both normal distributions for the average, and we can clearly see that the male average is higher, and so we can reject our null hypothesis that the average of BMI of males is lower or equal than the average BMI of females.
Our second scientific hypothesis states that eating habits are strongly related to the level of obesity of a person. Then we propose two statistical hypotheses. The first one states with its null hypothesis that the proportion of subjects that frequently eat high-caloric foods with any type of obesity is larger or equal than the proportion of subjects that frequently eat high-caloric foods without any type of obesity. Its alternative hypothesis states that the proportion of subjects with any type of obesity that frequently eat high-caloric foods is smaller than the proportion of subjects with any type of obesity that do not frequently eat high-caloric foods. Our second statistical hypothesis for the scientific hypothesis starts on its null hypothesis that the proportion of subjects with obesity that consume alcohol is larger or equal than the proportion of subjects without obesity that consume alcohol. Its alternative hypothesis states that the proportion of subjects with obesity that consume alcohol is smaller than the proportion of subjects without obesity that consume alcohol. For this hypothesis, we use the level of obesity, the variable FAVC, and the variable CALC. The frequent consumption of high-caloric foods FAVC variable has two possible outcomes, whether the subject frequently consumes these products or does not. And since we can consider each subject an independent event, this variable should follow a binomial distribution. Hence, we can follow a similar procedure as with the gender variable to compute the mean and the standard deviation. Taking into account the probability function for a binomial distribution on the top left, where n is a total number of observations and x is the number of people who answer that has a frequent consumption of high-caloric foods, we can differentiate the natural logarithm of that function and compute that the estimated proportion is 0.69. Then we can calculate the Hessian, which results in 2,366. Then, by doing a simulation by 1,000 resamples with replacement from the original data, as well as 1,000 randomly generated data from our v-norm function from R, and each sample having 490 observations, we can have the plot on the right. Our lower bound is the division of 1 dividing the Hessian, which is the line on the plot, and we can see that our data remains below of that line until around 700. Given that around 70% of the data remains below the line, we can say that our results are correct. By looking at the normal distribution for this parameter, we can see at the plot on the right that for this particular dataset, The proportion of persons who are not obese and have a frequent consumption of high caloric foods is larger than of those who are obese and have a frequent consumption of high caloric foods. Hence, our null hypothesis is rejected and we use our alternative hypothesis. Originally, the frequent consumption of alcohol variable, CALC, has four possible outcomes, which are no alcohol consumption, sometimes consumes alcohol, frequently consumes alcohol, and always consumes alcohol. And this could follow a multinomial distribution. However, even though the variable CALC has four different probable answers, it is possible to consider this variable following a binomial distribution by grouping these observations as consumes alcohol or does not consume alcohol. This way, we can follow a similar procedure as we did with the frequent consumption of high caloric foods variable. By performing the maximum likelihood estimator and the Kramers-Roa lower bound, we have that the estimated proportion is 0.64 and the Hessian is 2162. We validate these values by making a simulation of 1000 resamples with replacement from the original data and 1000 randomly generated data from the R-Vinum function from R. Once again, each sample had 498 observations. On the figure on the left, we first plot the division of 1 dividing the Hessian as our lower bound. And we can see again that 70% of the data is below that bound, which validates our results. Finally, we can see that the proportion of people who are obese and consume alcohol is higher than the proportion of people who are not obese and consume alcohol. Hence, our null hypothesis is not rejected.
Our last scientific hypothesis states that the use of electronic devices decreases physical activity. Therefore, it can be associated as a factor to increase obesity levels. And we formulated two statistical hypotheses. The first null hypothesis is there is no correlation between time using electronics and obesity levels, and our alternative hypothesis is there is a positive correlation between time using electronics and obesity levels. And for our second statistical hypothesis, our null hypothesis goes, there is no correlation between time using electronics and physical activity frequency. And our alternative hypothesis states, there is a negative correlation between time using electronics and physical activity frequency. In here, we can see a summary and a histogram of the information of our variable time using electronics. Since we have three different outcomes that can be considered independent, this variable should follow a multinomial distribution. And here we have the information regarding our variable physical activity per week. This variable should, as the last one, follows a multinomial distribution as well. To test both of these hypotheses, we will use the technique of regression. This requires to define our dependent and independent variables, to parse the categorical data into numeric values, 1 and 0. This process is called dummy coding, and it's necessary to enter our information into the model. And finally, to define our equation, which will have this form, where b0 is a constant, b1, b2, up to bn, and so are the possible outcomes each variable can have, and x1, x2, up to xn are the outcomes of the variable, 1 or 0. The correction, more detail, and improvement of this technique to test this hypothesis will be addressed in further presentations. Thank you very much for your attention.